All right, welcome to Thursday, week 4. Um, Hopefully, the ones that are not here are finishing up the test. I have not finished grading the labs or quiz 2 yet. I should finish those up after class tonight. I had something else. Oh, I don't remember. Anyway, so um, this week tonight we're going to be doing 3 sections. I know that's a lot, but in order to have office hours on the Tuesday of the test, I need to squeeze the whole week into one class. But still isn't completely overwhelming. It's just going to be a little bit longer and than normal. And then next week, both sections are pretty short. And so kind of make up for the little bit longer tonight. So tonight's going to feel pretty disconnected, but it will all tie together once we're in chapter 6. Chapter 6 will kind of tie it together. So we're going to talk about the different ways to compute probability. We're going to talk about the empirical method and the classical method. And then in section 5.1 is pretty short. 5.2, we're going to talk about the OR rule, which is the addition rule for things that are disjoint. We'll talk about the general addition rule, and then we'll talk about the complement rule. And then in 5.3, we're going to talk about AND events. You'll understand what that means in a little bit. And we're going to talk about how to determine if things are independent and what the multiplication rule is for those. Then we'll also look at least probabilities. So those are the things that we are doing tonight, and hopefully you'll find it easy and interesting. And it'll be a nice break. There's no fancy calculator functions. Basically, if you can do multiplication and addition, you've got it tonight. I mean, we'll be doing a little bit of exponent work, but that's about it. So it's pretty easy. I'll just jump right into it. Let me get my iPad to open back up. All right, maybe. Okay. So we're going to do a little bit of vocabulary here. And before we jump into things, this 5.1 is mostly vocabulary, a little bit of procedural, but it's mostly vocabulary, not a whole lot of math. So when we are talking about all of the outcomes, it is every possible thing that can happen for an experiment, every possible outcome. I'm not going to ask you to write the outcomes this way, but this is what it would look like. So if I wanted to know all of the outcomes of rolling a dice, I would have and I don't know why, I think it's like event one, but I don't know why it's event in this case, but this is just the way we do it. So first option is rolling a 1, second one would be rolling a 2, rolling a 3, a 4, a 5, and a 6. So there are 6 different possible outcomes, and this is each individual possible outcome. I am not going to ask you to relay this to me. On B, they want the set of all possible outcomes. This is the sample space. So in this case, similar to A, but it's just all put together. My sample space is 1, 2, 3, 4, 5, or 6. So this is something I will ask you. I will ask you to give me the sample space. The way that it looks is you're going to use these curly brackets. So my curly brackets look like this. They're not always pretty. And you will put all the possible outcomes. So if I was rolling 2 dice, for example, this is going to be a whole lot. This is going to be huge. Would never ask you to do a sample space, something this huge. But I would have the possible outcomes of 1, 1, 1, 2, because the first dice is 1, the second dice is 1. And the next one is the first dice is 1, the second dice is 2. Then I have 1, 3, 1, 4, 1, 5, 1, 6. Then I'd have 2, 1, 2, 2, 2, 3, 2, 4, and on and on and on until I get every single possible outcome. There would be 36 of them. I'm not going to ask you to do that with such a large number of possibilities. But if I was rolling 3 dice, it'd be 1, 1, 1, 1, 1, 2, 1, 1, 3, and on and on and on. And there would be so many. But I'm not going to ask you to do that either. That would be 216 possibilities. We're not going to do that. So this would be your sample space. So if I asked you, well, I have an example on the next screen, so I'm just going to stop there with that. Then defining the event. Defining the event is what would be a success. So with letter C, it's what would be a success. So if my event is roll an even number, so that big E is an event. If my event is to roll an even number, the successes would be a 2, a 4, or a 6. So if my event when I was pulling cards out of a deck, so if my event was to get to pull a king out of the deck, I'd have King of Hearts, King of Diamonds, King of Spades, and King of Clubs. Those would be my four successes. So you need to be pretty specific with it. But that's basically what that is. And it's also with curly brackets or with quotes. But definitely, I can tell you on the next test, you are going to have to list the sample space of something. It's going to be a small sample space. It won't be a very large one. I would not do two dice. I'm not going to do like two decks of cards or something like that, but there will be a sample space that you have to list. So it's just curly brackets and it's every possible outcome listed. All right. Oh, I did not open my chat. Knew something was missing. Okay. I don't know how I have this not set up correctly. There we go. Next page. So we have two different approaches. We have the empirical approach and we have the classical approach. They have other names also, and I'm going to tell you those other names because I frequently will call it by the other names. So the empirical approach is also known as experimental probability. And I frequently will refer to it as experimental probability because it is the way that I was taught it, and I had never heard it any other way until I started teaching this class. So, the empirical approach and experimental probability are the exact same thing. You are not going to be tested or quizzed on this vocabulary, so don't worry about that. What we do with the experimental probability or the empirical approach is you actually perform the trials. You will actually flip the coins. You'll roll the dice. You pull the cards out of a deck. Whatever it is that the experiment is, you are actually going to perform the trials. So in this case, let's say if we were rolling a dice 12 times, the number of trials, how many times you roll the dice would be your denominator. And then let's say that I was looking for an even number. I was looking for an even number and I rolled the dice 12 times. The top, the numerator is how many successes you have. So if I roll the dice 12 times and 5 of those times I get an even number, then it's 5/12. This is just basically a relative frequency. That is exactly what it is. We just are, this is just the probability with our experimenting. And the more times, and we're going to talk about this in a few minutes also, the more times I roll the dice, the closer you're going to get to the actual probability of it happening. This is our empirical approach. So we're using this probability. Based on this, the probability of rolling an even number is slightly less than half. But let's say that I rolled the dice 150 times or 1,000 times, then you're going to get closer and closer and closer to the actual probability, which obviously is 1/2. So that's called the law of large numbers, but we actually have a slide for that later on. So we're just going to kind of move past that. So the empirical approach or experimental probability requires you actually to complete the trials. Questions on that? All right, next one. Okay, so here is an example right here. So I don't know if you've ever played the Pass the Pigs game. It is pretty cool. I play it in my classroom when I'm teaching stats at the high school. Anyway, so you get points based on how the pig lands. And there's 6 possible ways that the pig can land, and these are all 6 of them. So a class of 52 students rolled the pigs 3,939 times. The number of times each outcome occurred is shown here in the table. And so what we're going to look for is our we're going to build a probability model. We are going to look at the probability of each of these happening. So where is my calculator? One of my grandsons likes to use the calculator and pretend that he's like taking orders on it. So I frequently find it in weird spots. He's adorable. Okay, so I'm going to take 1344 and you're going to divide it by the total number of pig rolls. And I'm just going to put that in my calculator. So I have about 0.34. So there's about a 34% chance of getting a side with no dot. I'm going to do this with each of them. It's about 0.33. I'm rounding to the nearest hundredth because it's just what I'm doing. About 0.19365 divided by 3939. 0.09. 137 divided by 3939. And then 32. 3939. There we go. So now I've built my probability model. Yeah, I know I rounded that last one to 3 decimal places, but I just couldn't not round it to 3 decimal places. And so then somebody could ask me about what is the probability of rolling a razorback. And you can look at this and say there's about a 19% chance of rolling a razorback. We did 3,939 trials. That's a lot of trials. So this is probably pretty close to the actual probability of this happening. So this would be our probability model. I'm going to tell you that there's the things that a probability model must have, and I think the next slide might tell me this, but I'm going to write it here anyway. So every probability, each probability is between 0 and 1. I'm just going to between 0 and 1. And, and it can be 0 and it can be 1, so it includes those endpoints. So they must be between 0 and 1. And then another thing is when I'm all done, they will all add up to 1. Because this should be 100% of the options. So all of the probabilities will add up to 1. Now, obviously, because of rounding, you might be slightly over or slightly under. I'm going to add all of these together. And let's see how close I am. Okay, so I have 0.988. And part of it, I think, is because I didn't round that last one. If I went rounded that one to 0.1, how would it be different? Let's see. Okay, so if I rounded it to 0.01 instead of 0.008, I'm at 0.99. So because of my rounding, I'm slightly off, but I would still say basically this adds up to 1. Because of rounding, we're slightly different. Now, if I would have ended up with 0.96 or 0.94, I'd be like, I probably did something wrong here, or, this is not really a probability model. Or if it added up to 110%, probably something's wrong. Another thing that frequently people miss is they'll sometimes have a negative, like trying to trick you. They'll ask if something's a probability model and you'll see one of the probabilities is negative. That can't happen. You can't have a negative probability. It's got to be between 0 and 1. So between 0 and 1, and they all add up to 1. All right.
Can I ask a question?
Yes.
Okay, so on the homework, the hand-in homework,
Uh-huh.
um, when we create a probability model, is it just filling in that chart?
Yes.
Or do we need to make like the sample set thing with the curly cues?
Nope. All it wants you to do is create this just like I did.
And then do you need to like add it all up and say that it comes close to one?
Nope. It doesn't tell you to do that. All you got to do is just calculate the relative frequencies.
Okay, great, thank you.
You're welcome. Okay. Uh-oh. I just did it twice. There we go. What the heck, man? I don't know what just happened here. Okay. Come on. I'm trying to be fancy here and paste it here, and I kind of did. So for now it's doing weird things. Okay, let's see. Okay. That's pretty darn close. We're gonna call it good. I don't know what happened when I pasted it. It's not supposed to cut everything. Let's try it again. Delete. Okay. I just want undo. I was trying to paste it so that it was all on there. Let's try it again. Copy. Let's see if this works. Paste. There we go. That works. Make it slightly smaller. This box is smaller, I think. I'm trying to be fancy and it's just not working. All right. So we already have our probability model. So we want to look at what is the probability that if we threw the pigs, if it lands on a side with a dot. So take a look right here. The probability it lands on a side with a dot is about 33% or 0.33. Now, when it asks if something is unusual, we're going to have to go into our Wayback Machine and think about the empirical rule. You may recall that anything more than 2 standard deviations away from the mean was an outlier. That 2 standard deviations on either side of the mean, that was 95% of our data, which means 5% of our data is in outlier territory. Therefore, anything that occurs less than 5% of the time is considered an outlier or unusual. An unusual outlier, those are the same thing. So it is considered unusual if it occurs less than 5% of the time. So take a look at leaning jowler right here. The leaning jowler happens just under 1% of the time. Therefore, it is unusual. It would be unusual to throw the leaning jowler. So anything less than 5% of the time is unusual. Same thing with the snouter. The snouter's 3%. Whoa, snouter's 3%. Therefore, it would be unusual as well. Questions on that? All right. So once again, we have a frequency table here. There's 200 people were asked their means of travel to work. I would like you to make a probability model for this one. I'm going to let you get started and then I will work quietly behind you. All right, how'd we do? Okay, so it now asks what is the probability that a selected individual would carpool to work? 200 people, that's a pretty big sample size. So I would say this is a pretty good estimate. So there's about 11% chance or 0.11 probability that a person would carpool to work. Now, when it comes to probabilities, I don't care how you answer. If you say 11% or 0.11, I don't care how you answer. Even if you said 22 200ths, I mean, I'd prefer you simplify your fraction. And on your hand in homework, please simplify your fractions for the final answer. But I don't care which way you answer. My open math has its own preferences, so pay attention to what they're asking for. But personally, I don't care. So if you say 11% on your My Open Math homework, that's fine. Or if you say 0.11, I don't care. Or if you said 11 100ths, I'd be fine with that too. So whichever you choose, my key that I use to grade it has all three answers. So you're good with either one. So this one also wants to know, would it be unusual to randomly select an individual who walks to work? So, um, walking to work, when we see here, walking is about 2.5%. Let me get a different color. About 2.5% is walking. Therefore, yes, it would be unusual. Oh, I forgot on B, it said to interpret the result on the carpooling. Basically, what that means when it says it just means that if I randomly selected any human in our population, there's about an 11% chance that person is a carpooler. But that's pretty much what B says. So I don't know exactly what they're looking for here. Questions on this before we move on? All right. So we're going to talk about the classical method now. Classical method, I call that theoretical probability. The other one was experimental probability. This is theoretical probability. That's just the way I learned it, but it's also known as the classical method. Nobody's going to ask you to use those definitions, but this is just what I call it. So, what's important for this one is that each outcome has to have an equally likely chance of happening. So if I had marbles in a bag and I'm pulling marbles out of the bag, every marble in the bag, each one has to have the same probability of being pulled out of the bag. So that's what it means with when we're using the classical method. We don't have to run an experiment. We just have to have the equal likelihood, or like rolling a dice. Each number on the dice has an equal probability of being rolled. And that's really what we need here. So this is what we do with the classical method or theoretical probability. So you have number of possible outcomes. So if we were looking at rolling one die, there's six possible outcomes because you can roll a one, two, three, four, five, or six. This is a standard six-sided dice. And if our event here was rolling an even number, there's three ways that we can roll an even number. Generally, we will simplify the fraction to 1/2. So the number of ways that we can get a success would be my numerator, and the possible outcomes is the denominator. So you don't actually have to perform the probability experiment. This is just based on how many outcomes are there and how many ways can you get a success. So this one is purely just math. And we have some examples. Now I'm letting you know my examples looks a little bit different than what you have on your um, printed out PowerPoint, but it's still dice and cards, but I have a different example because I didn't like that one and I changed it. So but this one's the same. So I have a fun-sized bag of M&Ms. There's 9 brown candies, 6 yellow candies, 7 red candies, 4 orange, 2 blue, and 2 green. So we are randomly selecting a candy. So even though there's different numbers of each color, every candy in the bag has an equal probability of being drawn out of the bag. So I'm going to count how many we have. So there's 15, 22, 26, 28, 30. So there are 30 candies. And the number of yellows I have is, where's yellow? There's 6 yellows. So 6 yellows out of 30 candies. So out of the 30 candies, 6 of them are yellow. Therefore, we have a 1/5 chance or 20% chance of pulling a yellow out of the bag. So the probability it's yellow is about 20%. So we're looking at the probability that it is blue. Once again, let's take a look. I have two blue candies. So 2 out of 30. 2 out of 30 is blue, which would be 1/15. I don't have that decimal memorized. And as soon as I put it in, I'm going to be like, oh, wait, I do have that memorized. So it's about a 0.07% chance. So about a 7% chance that it is blue. So yep, good. Except for you didn't round up, but that's okay. You're really close. I don't think anybody's going to get mad at you. So when it says to comment on the likelihood that the candy being yellow versus blue, all you want to say is you are 3 times more likely to get a yellow candy than you are to get a blue candy. It's no more deep than that. It's as deep as it goes. You're just 3 times more likely to get a yellow than a blue. I swear I remember a day when there were no blue M&Ms. I think that they were added later, but I could be wrong. But I'm pretty sure the blue ones were added later. I don't know. I could just be old and be thinking weird things. All right, let's talk about dice. Okay, so we want the probability of rolling a 7. I want you to try this one. Probability of rolling a 7, the probability of rolling snake eyes, which is rolling a 2, and then the comment the likelihood of rolling a 7 versus a 2. I'm going to help you here a little bit. The sevens are on a diagonal. They're on this diagonal, and there's 36 total here. 36 total possible outcomes. So there's the 7, and a 2 this is the only one right here. So we had to take a moment. Okay. Yep, you got it. Good. Good, good, good. Okay, now we want the probability of rolling a 2. You got that already. 1 out of 36. I definitely don't know that decimal. 0.03. So all at once, when you're commenting on the likelihood of rolling a 7 versus rolling a 2, all it wants you to say is you are 6 times more likely to roll a 7 than roll a 2. That's all it's looking for. Questions on this? Right, so now we're going to talk about if our events are not disjoint. So we're going to talk about if there's overlap. That's what we're going to talk about next. That's 5.2. Okay, so we're done with 5.1. If you keep track of that sort of thing, we're going to start 5.2 and we're going to learn about the addition rule. Addition rule is fairly simple, but there's a couple little points that sometimes people stick on, and I'm hoping I can catch those. So two events are disjoint if they don't have any outcomes in common. So if things are not mutually exclusive. So mutually exclusive means that so disjoint and mutually exclusive, sorry, are the same thing. Mutually exclusive thing means that they can't occur at the same time. I can't roll both a 2 and an odd number with the same roll because 2 is not odd, so I can't roll both of those. Or I can't be both 3 and an even number because they're disjoint. So disjoint probabilities are super simple. Gets a tiny bit more complicated, but not much when things aren't disjoint. Okay, I frequently call the addition rule the rule for or probabilities because when you see the word or, you are going to use the addition rule. If things are disjoint or they're mutually exclusive, you just add their probabilities together. Like, for example, that last one, the probability of rolling a 7 was 6 out of 36, and the probability of um, rolling a 2 was 1 out of 36. So if I added those together, the probability of rolling a 2 or a 7 would be 7 out of 36. You just add those probabilities together. So when they're mutually exclusive, it's super simple to do, just add them together. Now, if I had several different things, I can add all of their probabilities together as long as none of them have anything that overlaps. None of them have anything in common. So maybe I say the probability of rolling a 2 or rolling a 3 or rolling a 4, those are all disjoint things. I can add all of those three probabilities together. So however many you have, if you have 20 different pairwise disjoint things or things that have nothing in common, you can add them all together. So it's not just for two things, it's for as many things as you have that are disjoint.
Could you go back to the a couple slides ago for just a second?
Sure.
Yes, that one.
Okay. Yeah,
Thank you.
no problem.
All right, that's fine. Thank you.
Welcome. Okay. So we have a probability model right here. It shows the distribution of number of bedrooms. It says rooms, but it's number of bedrooms in a housing unit in the United States. So we're verifying that this is a probability model. And so look at all of our probabilities are between 0 and 1. Take a look at all of them. None of them are over 1. None of them are negative numbers. And they all add up to 1. So I already added them up and they add up to 1. So that's the first thing we're going to do. We did that. These things are clearly disjoint because a two-bedroom house is not also a four-bedroom house. In general, they're different things. Obviously, some people will be like, oh, yes, but I just converted this den into a bedroom. We're not talking about that. Okay. So next, we want to know the probability that a randomly selected housing unit has 2 or 3 bedrooms. So here's my here's my 2 bedroom, and here's my 3 bedroom. So I'm just going to take the two probabilities. So my probability of 2 plus my probability of 3. So it's going to be 0.032 plus 0.093. So that would be 0.125. Oh, good job. Thank you, Gwen. So there's about a 12.5% chance of randomly choosing a 2 or 3 bedroom housing unit. Questions on that? All right, I'm going to complicate it just slightly after we do this. I guess we're going to do this first. All right, we want to know the probability of the event drawing a king first. Then we want to know the probability of the event drawing a king or a queen or a jack. So this is what it's going to look like. So the probability of just a king, I'm just going to put a K because I can do that. Use a highlighter because I like highlighters. Okay, so probability of a king, just be these four. We all know there's 52 cards in the deck. I'm going to go back to a pen. So it would be 4 out of 52. Which I can simplify that fraction. 2 out of 26, 1 out of 13, or 1 divided by 13. About 0, whoops, dark on it. 0.08 approximately. So there's about an 8% chance of drawing a king out of the deck. All right, so now we want, good job, thank you. So probability of K or Q or Jack. So we have 452s plus 452s plus 452s. So that's 12 52s, 50 seconds, I guess you would say. So that would be 3/13. And I don't know why I mathed that considering it's because of the rounding on the last one, it's just 0.23 because I was rounding on the last one. So you have about a 23% chance, almost a quarter, um, to of drawing one of the face cards. Because there's no overlap on them, because if I'm highlighting them, there are no cards highlighted twice because you can't draw a king that is also a queen. You can't draw a jack that's also a king. There's no overlap at all. They are disjoint. They're mutually exclusive. You just add those together. Any questions on the mutually exclusive ones?
Yeah, if you have three things that are identical like that, my brain just wants to multiply it by three.
Well, you could
Does
have done
that
that. It's the same
work?
thing.
That
Multiplication
works
is
too?
repeated addition, so that's fine.
Okay.
Yeah, absolutely. Please do. But for teaching purposes, this is what I show. But yes, go ahead and just do that. Because that's what my brain did. I wrote 450 seconds plus 450 seconds plus 450 seconds. But in my brain, I just did 3 times 4. It's the same thing. All right. So when things are not disjoint, when they are not disjoint, you still add the probabilities, but you need, whoa, that's not a pen, that's a highlighter. You need to subtract the overlap. You need to subtract it off, and I will show you why in a minute. So you're going to take the probability of E plus the probability of F, and you will subtract the probability of E and F of both things happening. And I will show you why once we do an example. But this, at least write the rule down for now, and I will show you the why on it. All right, anyone need another moment? Okay, moving on. So now we're going to compute the probability drawing a king and a diamond. So I'm going to write this down. Probability of king or diamond. Really ugly writing. Okay. So I'm going to show you with highlighter. So here's the king. We already know that that is 4 of them. I'm going to write that down. We're going to keep it in 50 seconds until till the end. So we know that's 4 50 seconds. Now I'm going to highlight diamonds. Now I just highlighted the diamonds. That was pretty. Okay, plus 13 50 seconds. Notice this one right here. This one right here. I highlighted it twice. So I counted it in both the kings and in the diamonds. I highlighted it twice. Therefore, I need to subtract one of them away. That's the overlap. That's the and. Because I highlighted that one 2 times, I have to subtract one of those times that it was highlighted. So I have 4 plus 13, so I have 17 minus the 1 gives me 16 out of 52, which is 8 out of 26. So it's 4 out of 13. Or we had that probability back here. 4 out of 13 was about 20. Oh, we had a 3 out of 13. So it's about 31%-ish. Yep, exactly. Good job. So I just rounded to 2 and you rounded to 3, but yours is more accurate than mine actually. So that's why we have to subtract the and part because that's where they overlap. We're just subtracting the extra one that we counted. Questions on this before you guys try one on your own? The next question is the one that's different on your PowerPoint. So we rolled a pair of fair dice. We want to know the probability of rolling a multiple of 6 or rolling doubles. I am going to circle them for you and then you can calculate it. Multiples of 6 is we have 6 and we have this 12 over here. There's our multiples of 6. And I'm going to use a different color. Let's use hot pink's probably a good one. So rolling doubles. So my doubles are, I have this one. My doubles are on this diagonal. I guess I could have done it different. Hold on. Okay. My doubles are on this diagonal. There we go. So we want the probability of rolling 6, a multiple of 6, or rolling a double. Go ahead and calculate that. Okay, so I have 6 of 36 plus 636 minus 2. So 12 minus 2, so I have 1036. Did you get a different, did I count them wrong? You have a different number than I do. Okay, there we go. All right. So
I accidentally used 52 as my numerator instead of 36.
oh, okay. I was like,
Yeah,
because
I
I
fixed
was
it.
believing you were correct. I was believing
Nope,
you're correct.
nope, I fixed it.
I was questioning myself there for a second. All right, so yeah, about 28%. So 5/18 or 28%. So you have about a 28% chance of rolling a multiple of 6 or doubles. Any questions on this? Fairly straightforward so far. I know it's always straightforward during the lesson, and then you get to the homework and you're like, wait a minute. Maybe I don't get it. It's okay. Good thing I try to answer messages as quickly as I can, but I go to bed early because I wake up early. So I don't answer them late at night, but you might get a message back from me fairly early in the morning. Okay. So this is the complement rule. The complement rule turns out to be something really, really important later. It's going to start off super simple, but it's going to be your best friend as we move forward. So, especially when we get to chapter 6. So, the complement rule just means the probability of something not happening. So, like if the probability of rolling a 6 on the dice is 1/6, the probability of not rolling a 6 would be 5/6. So, it's just like the opposite. It's just the complement rules, the probability of something not happening. So, for example, if the probability of, so according to the American Veterinary Medical Association, the probability, or 31.6% of households own dogs. What's the probability a random selected household doesn't own a dog? So if my probability of owning a dog is 0.31, so probability of owning a dog is 0.316, not owning a dog is 1 minus 0.316. So it would be 0.684, or about 68.4% chance of not owning a dog, of choosing a household that doesn't own a dog. So this complement rule is going to become your best friend later on. Trust me. So sometimes we use the complement rule because we don't want to add a whole bunch of stuff up. So like in this case right here, it doesn't actually ask the question that it's supposed to ask. But there's 318,800 residents in Hartford County. We want to know the probability that somebody will have a commute time. So if I want to know the probability of somebody having a commute time of less than 90 minutes, so here's the probability for 90 minutes. And I want to know what's the probability someone will have a commute time of less than 90 minutes. I don't want to add all those things up and then and take that probability. So I would just do 1 minus 0.015 because that's the probability of over 90 minutes. So I'm going to do 1 minus 0.0684. 5. Whoop, that's the wrong number. 1 minus, I was using the old number, 0.015. Yes, I don't know why I didn't do that math in my head, but you are absolutely correct. 0.985. It's about a 98.5% chance that people would have a commute of less than 90 minutes. We frequently use this to save ourselves a little bit of work because don't we all just have a little bit of lazy in us? Every single one of us has a little bit of lazy. I know I do. I'm going to do math the easy way most of the time. Some of the more difficult ways are fun, but yeah, but I'm also weird. I love math. I happen to major in it. So that right there tells you I'm strange. And I'm a little kooky. Anybody who majors in math is a little bit crazy. All right, questions so far? Are we doing okay? All right. Okay, so this is the easiest one. You just do this in your head. If 25% of a deck of cards is a suit of hearts, what's the probability you will not draw hearts? Exactly. See, you had it typed out before I even quit reading it. So 1 minus 0.25. So the probability of not hearts is 0.75. That's usually how I write it. I'll just say probability not hearts. Or like when we're talking about probability somebody survives something, I'll say probability not survived or probability not vaccinated. It's usually how I do it. Questions so far? So I believe we're going to jump into 5.3 now. All right. Yes, we are. We are now in section 5.3. If you keep track of that sort of thing, you are done with 5.1 and 5.2 and have everything you need to complete those homework assignments. Okay. So you can put 5.1 and 5.2 in your pocket, and we're going to jump into the and probabilities. The and probabilities are going to also be helpful to help you find overlap when you're looking to subtract things away. Okay, so two events are independent if the probability of one thing doesn't affect the probability of the other. Two things are dependent if one probability will affect the other probability. So for example, if I have a deck of cards and I say, what is the probability I pull a king, and then I'm going to pull the king out. Now that the king is out, I can't now calculate the probability I now draw a queen isn't the same as it would be before. It is dependent on whether or not I got a king the first time. Those two things are not independent. But if I'm pulling them out of two different decks, they're independent because they don't affect each other. So I'm going to give you some better examples here. Okay. So letter A, suppose you draw a card from a 52 card deck and then roll a die. These events, draw a heart and roll an even number, they're independent. The results of choosing a card don't impact the results of the dice throw. Unless you put the card on the table and you throw the dice and it hits it or something, but in general, they do not affect each other. Although this one is the A and or B and C are kind of interesting. So suppose two 40-year-old women who live in the United States are randomly selected. The events woman 1 survives the year and woman 2 survives the year. Those are independent. You are not likely, if I took all 40-year-old women in the whole US, if I randomly chose two of them, they're not likely to know each other. There's enough of them out there that those two women are not likely to know each other or have anything in common or affect each other at all. However, letter C, Suppose two 40-year-old women live in the same apartment complex. The events woman one survives the year and woman two survives the year. Those are dependent. They're going to be driving their cars out of the same parking lot. They're going to be using the same stairs or elevator. One of the women can fall asleep with a cigarette and light the whole thing on fire. One of them could drop something in the hallway and the other one could trip over it. Because their lives, even if they don't really know each other, their lives can intersect. We have to say that they're dependent. Because they're kind of in each other's world in one way or another, they're too close to each other to call it independent. Does that make sense?
So I'm struggling a little bit.
Okay.
Um, how far apart would they need to be? Like if it's two apartment complexes over or the same city, or I guess I can't wrap my head around it yet.
I wish I had a good answer for you. I wish I did. I
Mhm.
don't have a good answer for you. I think that if you're doing the math, I would say if you can reasonably state that they probably don't have anything to do with each other, because we don't deal with absolutes around here. So I
Yeah,
think if you just can reasonably state that they don't have anything to do with each other or aren't in each other's lives or area at all.
like they're in an enormous apartment complex building that has 2,000 residents and are randomly selected. They might be independent.
I don't even know if I would say that, but like for example, two people randomly chosen in Medford, I'd probably say you're fine calling them independent. But two
Okay.
people that live on the same street in Medford, probably not, because they're both going to be leaving this, driving down the same street.
Okay.
And I know this is terrible because, but we don't deal in absolutes. So there's
Yeah.
not like this one rule. But I
Okay.
think it's just if you reasonably can expect. Yeah. So I'm sorry.
Okay. Okay.
I wish that I had a really great rule for that, but yeah. That was the first time in all my years teaching this, the first time anybody's ever asked me that question. So if nothing else, you get a gold star for that. All right. So let's take a look at this. Think about these in your head. Suppose you flip a coin twice, the same coin, you flip it twice. The first flip, it lands on heads. Second flips, it lands on tails. Do we think this is independent or dependent? It's definitely independent. Because one flip doesn't dictate what happens to the second one, unless maybe the first flip it landed in some grape jelly, and then when you flipped it again, it made one side heavy, but otherwise, no. So, are the events earned a bachelor's degree and earned more than $100,000 per year? Do you think those are dependent or independent? Think about those. Yes, they're definitely dependent unless it'd be, yes, especially, I mean, a teacher earning a bachelor's degree is not going to be $100,000 per year. So maybe those are independent, but normal people, they just don't pay teachers that much. Actually, I think California and New York, I think if you've been teaching enough years, you can earn over 100,000, but their cost of living is outrageous. Sorry. Okay. Two 24-year-old males in the United States are chosen at random. Male one gets into a car accident during the year. Male two gets into a car accident during the year. Are these events dependent or independent? Right, they're independent because we're not likely out of the whole US to choose two 24-year-old males that are in each other's lives. I mean, it could happen, but it's not likely. Questions about this other than the obvious one that I was really not able to answer? I'm going to look that up though. If I can find an answer for you, I will post it in the forums. So I'll keep your eye out. I'm going to see if I can find that answer. But other than that, are we feeling good? Okay. All right. Here is our multiplication rule. The events must be independent. They must be independent. The multiplication rule is for and events. So if I talk about and probabilities, I'm talking about the multiplication rule. So the or probabilities is the addition rule, and probabilities are the multiplication rule. Give you a second. Okay, moving on. All right. So this is where we're going to get, oh, not yet. The at least probabilities are where it gets kind of cool. All right. So the probability a randomly selected female aged 60 years old will survive is 99.186%. What is the probability two will survive? So the probability the first survives is 99.186%, and the probability the second survives is 99.186%. So you just multiply those two numbers together, the two same numbers together. So we're getting 98.38%. So each of those are independent. So they have their own independent number. I mean, it's the same number, but each one has that 99.186% chance of survival. It's actually a pretty good chance. I bet 50 years ago, it probably wasn't that high. All right. You flip a fair coin twice. You want to know the probability you obtain a heads on both flips. I'm going to write all the stuff out. I know you probably could just really quickly get the answer, but I'm going to look probability heads and heads. So the way that we do this is probability first heads times the probability. See, you already have it. I haven't even finished writing it. Second heads. So you would do, I don't even need to math it like that. 0.5 times 0.5. You are right. It is 0.25. So the probability that both of them are heads is 0.25 or 25%. Questions so far? All right. I'll give you a second if you're writing down all my things. I just basically try to write it down like so it looks good for notes. So if you look back later, you're like, okay, that's exactly what happened. It's that whole teachery thing that I do. All right. I love these ones because this is what happens. This is like totally true to life. Manufacturer has exercise equipment. They know that 10% of their products are defective. They also know that only 30% of their customers are actually going to use the equipment the first year after it's purchased. There's a 1-year warranty on the equipment. What a proportion of customers will actually make a valid warranty claim? All right. So what we need to do is we need to look at the probability defective and used. So we're going to do the probability it's defective times the probability it is used. So 0.10 times 0.30. Uh-oh. So it's 0.03. Look at you doing it in fractions and stuff. That's crazy. Perfect, though. That's good. That's good. Okay. So we have about a 3% chance that the product is defective and it was used within that first year. So companies frequently will do this. They're like, do I spend the money that it's going to cost to fix whatever this thing is that's defective? Or test every single one of them to find out if I have it, if they're defective. Should I spend that money or should I gamble on whether or not people are going to actually use the product and whether or not they're going to get a defective one? Because I bet that there could be even something else on there and say that only, maybe only 50% of those who get a defective one will actually try to use the warranty. Because I know personally, a lot of times I'm like, this is just too much work to even try to get my money back or return it or whatever. So I'm just going to take the loss. Many people will just take the loss or try to fix it themselves. So I bet this number would even be smaller. Who is actually going to try to use their warranty, make a warranty claim? So companies will do this. They will actually say, oh, this is worth it to me. It's not going to cost me very much. It'll cost me more to test all these machines. So this is real math. Any questions so far?
Not that I think this is every appliance in my house right now.
Totally get that. I totally get that. All right. Okay. So I want you to try this one. Go ahead and try this one. So this is four of these randomly selected 60-year-old females. It's the same thing we did before, but with four of them. I'm working quietly behind you. How'd we do? So there's about a 71% chance that all four women will survive the year. Now, you may have thought about this, and I'm going to say it before you ask me because I know that one of you has this in your brain to ask me, yes, you can do this. Wait, hold on. To the fourth power. Absolutely. Absolutely do 0.99186 to the fourth power. If you don't know how to raise things to the fourth power in this calculator, it's this button right here. You would put in 0.99186. This right here, that's, whoops, let me make it prettier. This is called a caret, and that's going to turn it into an exponent for you. It's so much faster. So yes, you absolutely can just use an exponent. Because what if I asked you the probability that 18 would survive the year? You definitely don't want to multiply this out 18 times. Because I can tell you that if you're anything like me, you would lose count putting them in your calculator. So you
I'm not,
absolutely
I'm
can.
not sure I'm doing it right. I'm getting a different answer. I'm getting 0.9678.
Oh yeah, you have a different answer than me because I typoed in my calculator. I just looked at my calculator and yes, I typoed. I didn't put the second nine. I didn't put the second nine. Yep.
I was worried I didn't understand it. Okay,
No,
great.
this
Thank
is totally on me.
you.
Okay, there you go.
Phew,
Better?
much better.
Sorry about that. All right. Questions on this? Are we feeling okay? We only have two more slides. Y'all are doing awesome. Okay. We're going to do at least probabilities. Before we get over there, I'm going to tell you the at least probabilities are the ones people struggle with the most in this section and in the next, and in the chapter 6, letting you know that at least probabilities are, I'm not sure why, but it is where people struggle the most. And I do my best to help, but if you struggle with this, don't feel like you're the only one. Ask the questions. If you need to ask me the same question 5 times, go for it. You're not bothering me. The at least probabilities are where people struggle. Okay, so I'm going to tell you every time you see the words at least, you will use the complement rule. I'm going to write it up here because this is important. Every time you see the words at least, use the complement rule. And I'm going to put some exclamation points just because. Not yelling at you, just saying, emphasizing. Every time you see the words at least, use the complement rule. Every time, without fail. Now I'll show you how to do this. So I want to compute the probability that at least one male out of 1,000 aged 24 years and up will die during the course of the year if the probability that a randomly selected male survives is 0.9986. We want to know the probability at least one dies. What this means is not all 1,000 are going to survive. So the probability at least one dies is the same thing, probability not 1,000 live. So we're looking for the probability that not all 1,000 live. So what it's going to look like is this: 1 minus the probability all 1,000 live. So it'll look like this: 0.9986. I'm going to put it in parentheses just because it looks better, to the 1,000th power. Because 0.9986 to the 1,000th power is the probability that all 1,000 live. So I need to do 1 minus that. So put that in your calculator. 1 minus 1, 1 minus 0.9986 caret. Let's hope I actually put it in my calculator correctly this time and didn't typo. Tell me if you got the same number as me. Okay, good. So there's a 75% chance that at least one of these 1,000 men are going to die within the next year. I know this is really morbid, but most of the things stats are used for in like corporate world, a lot of it is in insurance, and a lot of it has to do with calculating risk, which is like actuaries, they make good money. I actually considered becoming an actuary because they make really good money. They So basically what you do is you sit around and you calculate the probabilities and risk and things like that for insurance all day long. That's what you do. That's what an actuary does. But all right, we're going to do another one, I
I do
think.
have a calculator question real quick, if you could go
Yes.
back. So I'll tell myself I didn't know how to do the caret
Mhm.
square root part until I asked my teenage daughter yesterday. And she thought that the 1,000 should go inside the parentheses. Does it make a difference?
It will make a difference because the thing that I'm multiplying 1,000 times is the 0.9986.
Mm-hmm.
It says 0.9986 times 0.9986 times 0.9986 1,000 times. I'm not multiplying 1,000 by itself.
Mm-hmm.
I'm multiplying the 0.9986 by itself 1,000 times.
So I did it both ways and it came up with the same answer the same way, but I guess I just don't know which way.
Okay.
I don't even know what I'm asking.
I've never even tried that. Raised to the 0.9986. No, I got a very different answer.
Did you?
Yeah.
Okay.
And the
That's
answer
right.
the
So
answer is
parentheses and then
990.
a
So,
1,000 on the outside,
right,
but the caret raised first.
right. So that multiplying 1,000 to the 99.9986 power, you get 990. So clearly that's not a probability because it's greater than one. So that's gonna how you're gonna tell yourself, see that you did it backwards. So
Okay.
whatever the decimal is, that's gonna go in the parentheses. And the whole number is what's gonna be the exponent. Does that help?
Yeah, I think so. Thank you.
You're welcome. Okay, we're gonna do another one of these. Okay, 29 among 21 to 25-year-olds, 29% have said that they have driven while under the influence of alcohol. Suppose that three 21 to 25-year-olds are selected at random. What is the probability at least one of them has not driven under the influence of alcohol? I feel like with these, it's kind of important to write it out because they become very confusing if you're just looking at them. If you can figure out what you're looking for, it's helpful. So what I'm looking for, at least three have not I try to simplify my writing a little bit. Have not DUI'd. So at least, wait, sorry, at least one. Sorry, man, what's my problem here? At least one has not. At least one has not DUI'd. So I'm looking for probability, not all three DUI. It's one minus probability, all three DUI. How'd we do? Good? Right. So before we wrap up, this is the last slide. So before we wrap up, I'm going to show you a homework question that has the at least that causes people trouble every single time. So I'm going to pop over there. That is a lab. That doesn't help us at all. Okay. So I believe it's 5.3. Okay. There's a vaccinated, this one right here. Okay. So this one says in a large population, 60% of people have been vaccinated. If three people are randomly selected, what is the probability at least one has been vaccinated? So what you are looking for is the probability that not all three have been vaccinated. So you need to do one minus the probability that all three of them have not been vaccinated. So you're going to need to take this 60% and subtract it from 100% first, because you need one minus the probability all three are unvaccinated. Does that make sense? Will it help if I write it out? Okay, I'm going to write it out, and then I'll pop over to the other page. I'll pop over to my iPad. At least one vaccinated. Looks like, okay. Uh-oh. Okay, I'm going to pop over to my other screen. Okay, so we take the probability at least one vaccinated. It's the same thing as the probability that not all three are unvaccinated. So it's one minus the probability all three are unvaccinated. Hopefully that'll help you get through that. This is the one that most people struggle with. The at least probabilities, they're usually the biggest trouble in this section. If you can get down the at least, get those down, then you are well on your way to doing absolutely wonderfully on chapter 5 and chapter 6, because we're going to build on this in chapter 6. Okay, so that's the last of the new material that I have tonight. Any questions for while we were still being recorded? Okay, I'm gonna turn off the recording.